Hello, everyone. The title of our paper is Real-Time Dense 3D Reconstruction and Camera Tracking via Embedded Planes Representation. Firstly, let's look at the challenges of the RGB-D reconstruction. The first one. The camera pose evaluation is easy to slide in the textureless plane areas, which leads to camera pose evaluation error. The second one, the accumulation of the camera pose evaluation error will lead to camera drifting, as shown in the figure. In the indoor environment, there are a large number of textureless planar areas. When the camera skims these areas, it is easy to introduce the camera pose evaluation error. After a period of time, the error accumulation will cause the evaluation camera pose to deviate from the real camera pose more and more far away. In the man-made environment, the planar structure is everywhere. If we can establish the plane correspondence relationship between frames, then make the corresponding planes align with each other in the camera pose evaluation, we can effectively reduce the camera sliding in the plane area during the camera pose evaluation. How can we quickly and effectively establish the corresponding relationship between the planes in different frames? When we extract the plane in a point cloud, all points belong to the same plane projected into the parameter space will fall onto the same point. Based on such an observation, we can project all the planes in the frame into the plane parameter space to get a point cloud. Each plane in the frame corresponds to a point of the point cloud. In this way, we can transform the plane matching problem between frames as a point cloud matching problem by reducing dimension. Given two consecutive RGB-D frames, we first extract planes in each frame. Then we project all the planes to the plane parameter space to generate two-point cloud. Then we register the two-point clouds to establish the correspondence between them. The corresponding relationship between planes are obtained by the corresponding relationship between point clouds. After we obtain the plane corresponding relationship, we can use the plane consistency as an additional constraint to improve the camera pose evaluation. The contributions of the proposed method. The first one, we propose a novel method to establish plane correspondences between different frames using point cloud registration in the plane parameter space. The second one, we introduce a frame-to-frame plane constraint and a frame-to-model plane constraint to the traditional ICP camera tracking method, which makes the depth camera tracking more robust. The third one, we introduce a global plane map to manage all the planes in the reconstructed scene incrementally, which can significantly alleviate the cumulative error of the depth camera tracking. This is the pipeline of the proposed method. When we attain the new RGB-D frames, we extract planes in this frame. Then we project all the planes into the plane parameter space to generate the corresponding point cloud. Then we register the point cloud with the point cloud corresponding to the previous RGB-D frame and construct the plane correspondences between consecutive frames. At the same time, we align the point cloud of the current RGB-D frame with the point cloud corresponding to the incremental reconstructed model, and establish the plane corresponding relationship between the current frame and the reconstructed model. Then we use the local plane correspondences and the global plane correspondences to construct the plane consistency constraint and the global plane consistency constraint to the accuracy of camera tracking. Finally, a more realistic 3D model can be generated. The detailed steps to establish the correspondence between planes through point cloud matching. After we get the local plane correspondence and the global plane correspondence of the current frame, we construct the objective function to evaluate the camera pose of the current frame. This is the geometric consistency term, which represents the standard ICP camera tracking between consecutive frames. This is the local frame-to-frame plane consistency constraint term, which makes the corresponding planes between consecutive frames align as much as possible. This is the term of the global frame-to-model plane consistency, which ensures the corresponding planes between the current frame and the global plane map aligned as much as possible. We use the Gaussian-Euro-Newton method to solve this equation to obtain the camera pose of each frame. Then we fuse the depth data in the global model using the camera pose of each frame to reconstruct the model. Now we're going to show some experimental results of our method. The data sets in Table 1 contain planar structures, lacking geometric details or texture details, even lacking both of them, which are very challenging for current SLAM and reconstruction algorithms. The data sets in Table 2 are not specifically designed for evaluating structure-based SLAM methods. It shows some more general indoor environments. From tables, we can see that our method performs better on most data sets than the other methods. We compare the reconstructed results and camera trajectories of the proposed method with elastic fusion and ORB-SLAM2. From the evaluated camera trajectory, we can see that the estimated camera pose of the proposed method is more accurate than elastic fusion. Although ORB-SLAM2 shows better performance on the texture-rich dataset, such as Fig. A, camera tracking failures are prone to occur in plane scene without textures, as shown in Fig. B. In contrast, our method is able to reduce the accumulation errors that benefit from the planar constraint of the global plane map. The reconstructed results of our method in the comparison between our evaluated camera trajectories and the ground truth from the TUM RGB-D dataset. We performed comparisons of the proposed method in 3 cases including A, without plane constraints, B, with only the frame-to-frame plane constraints, and C, with joint the frame-to-frame and the frame-to-model plane constraints. For case A, the accumulative errors will be very serious in scenes where texture and geometric details are lacking, as shown in Figure A. When we add frame-to-frame plane constraints, the camera tracking accuracy will be improved. However, when there are fewer planes in the scene, the camera tracking will slide easily and produce cumulative errors, as shown in Figure B. When the frame-to-model plane constraint is added, the camera drifting can be effectively alleviated, and the camera sliding can be prevented. The tracking accuracy of the camera is greatly improved, as shown in Figure C.
This is the demo of the proposed method.
That's all. Thank you.